Our next unit is going to be on electrons and periodicity, and we'll start off talking about the electron and where it is in the atom and how it works. This is going to be part A of this lesson. I've divided it into two sections, mostly for ease of use. This first part is mostly going to be on more of the theory of the way the electrons are set up, and the second part is going to be more on electron configuration and how to actually calculate that for different atoms. So in this lesson, we're going to talk about two basic things. We're going to talk about the quantum model of the atom, and we're going to talk about orbitals, shells, and subshells, and suborbitals as well. So first thing we're going to talk about is the quantum model. Now, the traditional way that most sort of elementary science classes tend to be in this idea that you have a nucleus and you have electrons which orbit around that nucleus, like planets around the sun. And this type of way of looking at things is called the Bohr Model, named after a man by the name of Niels Bohr. Niels Bohr was I think a Dutch or Danish, I'm blanking on it right now, but he was a scientist that basically made some discoveries about the way that atoms worked, and he basically made an assumption, and he said that some things would make sense if you imagined the electrons being in orbits. It turned out that within the next 15 years or so after he discovered that, is that they had discovered enough other information to find that his model was basically incorrect, that electrons do not orbit the nucleus in the way that planets orbit the sun. They instead are going to fit a model which is called the Electron Cloud. And so the Electron Cloud is sort of the actual way that atoms work, or that electrons work. In order to understand this, we need to talk a little bit, as said, about quantum mechanics. Quantum mechanics is a part of physics that was developed mostly in the 1920s. It still comes since then. It's probably the best experimentally verified theory in all of science. But it says some things that are quite counterintuitive. And one of the things that it says, and this is where it comes into electrons, is something that says that you can't know the exact location and the exact momentum or exact speed of a particle at the same time. Is that, in fact, you can only know them to a certain amount of precision. Is the better you know where it is, the less you know about how fast it's going. And the better you know about how fast it's going, the less you know of where it is. And so, as a result, electrons don't actually exist in any one place. It's not like you can say, like the planet Earth is right here, is that in an atom, the electrons are in some region that all we can say is there's a certain probability of them being in a certain region. And this area of probability they call the electron cloud. It's not an actual cloud, it's not a fuzzy cloud like you see in the sky, it's a description of the probability of finding the electron. And it turns out that the electron sometimes has a high probability of being located in one place and a low probability of being located somewhere else. And it's a way of showing a diagram of that. We will show you, or I will show you some electron clouds, some diagrams of electron clouds for different electrons in a little bit. But you simply just have to remember is that whenever you're talking about the electrons around the atom, we really can't say exactly where they are. All we can do is we can say there's a good chance it's located around in here, or a 90% chance it's located in here, or a 70% chance it's located here. We actually can't say there's a 100% chance of it being located anywhere, because these quantum mechanical rules basically keep it from being located anywhere. If you said, I know it's not, I know it has to be here, then it could be going any speed it wanted to, and so it wouldn't be there anymore. So in a sense, it's we simply have to describe them as probabilities. And so that's what the electron cloud is. Now, that doesn't mean we can't say anything about where they are. And so that's where atomic orbitals come in. We talked about the Bohr model, and he talked about the things were in orbits. And so instead of that is they said, well, things still act a little bit like they're in orbits, but we know they're not actually in orbits. So they called them orbitals, in order to basically understand this a little bit better. And so atomic orbitals basically work like this. Is the first part deals with energy levels. Is that if I have a positive proton, and I put an electron near that electron generally wants to get as close as possible as it can to the proton. And so it will take the energy level which is at the lowest level, and so it'll get as close as it can. Turns out it can't get all the way to it. There's some reason, once again, some quantum mechanics reasons on why it can't, but it can get fairly close. The next electron I put in is going to also try to get as close as possible. But as I add electrons, it gets to the point where that first energy level, that first set of levels which is closest to the bottom, almost like a bookshelf that only has so many spots you can put books on it at the very bottom, as you go ahead and keep adding electrons to it, eventually that one fills up. It has to go to the next energy level, and so on and so forth. And so as we add electrons, is that they are going to go into different energy levels. And as it turns out, is that as we add electrons, they don't just go into different energy levels, they also go into different orbitals. An orbital is a particular type of region where electrons go into. And so let's take a look at some of those. So the atomic orbitals, there are 4 common ones, which are called the s orbital, the p orbital, the d orbital, and the f orbital. There are actually ones beyond this. They just go up by the letters after f, so G, H, I, J. We're pretty much only going to use s, p, d, f, and occasionally G. And to give you an idea of how this works, go ahead and take out your periodic table. And I've got one on the screen. Doesn't have the elements listed, but it will give you a decent idea of how this works. So the first thing is, if you look at the periodic table, you'll notice that there is sort of on the left side, there's sort of a tall block that goes here. This is oftentimes called the S block. Reason why it's called the S block is because as we add electrons that are the newest electrons to these elements, is they enter what is called the S orbital. The s orbital is the first one to fill. And so with hydrogen is that we add 1 electron, it's going to be in the s orbital, it'll be in the 1s shell. And so we'd say that we've got that. So we then add another electron that would go into helium over here, because that would have 2 electrons to be helium. That's also in the 1s. But then once we've got there, the s orbital is now filled. And so since the s orbital is filled, the 1s orbital is filled, it then has to go to the 2s. And so now we're in the 2s orbital. Add another electron, we're still in the 2s orbital. Add another electron, now we're in the 2p orbital. And so we go 2p, then another one, 2p, 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 and now the 2p is filled, and so it goes to the 3s. So then from the 3s, then add another one to the 3s, then to the 3p, and so on and so forth. Now, as you sort of look at this, we then go sort of through the 3p. After the 3p is the 4s. But then what happens? We go to a new section. This is the D block. This is this middle section right here. But if you notice this, it doesn't start with 4, because we had 4s. This isn't 4d. It's actually 3d right here. And so this has to do with the way it fills, and we'll talk about that in a second. So it'll fill up the D, 3d, then the 4p, and the 5s, the 4d, the 5p, the 6s, and if you look at your periodic table, this element right here would be what you've got on there as being barium. Barium's 56, the next number would be 57, and then 58. Where are those two? 57 is next to it, but 58's down below it. It's down here. And so this right here, after it fills the 6s, it's then going to fill the 4f. Then back up to the 5d, the 6p, the 7s, and then it's back down to the 5f, then the 6d. It isn't on here, but then it'll fill the 7p, then the 8s, and then actually it would go and it would fill the 5g, which would be something like way down here, then the 6f, the 7d, and the 8p, and so on and so forth. That's sort of the little more detailed way of looking at it. But these would be the basic atomic orbitals that you would see with this. This is how they fill. And so the next question would probably be, okay, so what exactly are these? And so we know that the s orbital fills first. So let's take a look a little bit at what we might get here. So some basic definitions that we have here. We talked about energy levels. And so energy level would be like the first energy level is the lowest energy level that you have. The second energy level is the next energy level. The third, the fourth, the fifth. These are basically like shelves. You know, you have a shelf at the bottom, and then you have a shelf going up and going up and going up like that. The shells themselves basically are going to be the particular part of the orbital that's in that energy level. And so the 1s would be a particular shell. It would be the 1s shell, the 2s shell, the 2p shell. So the 2s shell and the 2p shell are both in the second energy level, but they're two different shells. Now, within each shell, you have different orbitals. I'm sorry, I was a step ahead of myself there. The shells are the energy levels. So you have the first shell, the second shell, the third shell. Those are the same as the energy levels. Subshells are the 1s, the 2s, the 2p, like that. So in the second energy level or second shell, there is a 2s subshell and a 2p subshell. I'm sorry about that. So that's how that's going to set up right there. Now within each subshell, there are a certain number of suborbitals. Now, basically, if we take a look, going back for a section, we'll see that how many electrons fit into the s orbital. We go 1s, and then another 1s before we go to 2s. Then 2s, then 3s. There are always 2 that fit in to our s orbital. So the 2s, or the s orbital, is considered to have one suborbital. Each suborbital always fits 2 electrons. The reason why is that electrons can have 2 types of spin, either spin up or spin down, and you can't manage to put 2 electrons that have the same direction of spin in the same suborbital. But you could put an up and a down, and then that's all you could do, because if you try to put another down, there'd be 2 downs. You can't do that. Try to put another up, there'd be 2 ups. You can't do that. So each suborbital has 2 electrons that'll fit into it. The s orbital has 1 suborbital. The p, though, we have a 2, a 2, and a 2. 6 total electrons, 3 suborbitals. The d has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 total electrons. 2 per suborbital would mean it has 5 suborbitals. The f has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So 14 electrons, 2 per suborbital, so therefore it would have 7 suborbitals. So taking a look at this, what you can sort of see is that we said S had 1 suborbital, P had 3, D had 5, F had 7, G, we didn't talk about, has 9. What do you think H has? 11. And so what happens as we go is it always goes up by odd, the number of suborbitals goes up by odd numbers. And so we've got that. Since there are 2 electrons per suborbital, that means that the number of suborbitals is always half the number of electrons. So 1 suborbital means 2 electrons in the s orbital. 3 suborbitals in the p means that means there are 6 electrons there. 5 gives you 10 for D, 7 gives you 14 for F, 9 gives you 18 for G. And so that gives you an idea on how that works. Now the other piece that we talked about before dealt with which ones sort of happened in order. Because remember we got down to here and we said we had 4s, but then we had 3d. And so the question is, why is that? And so the reason why is because for your orbitals, the first s is the 1s orbital. You can sort of see that right here. Is the first time it fills, it's going to be the 1s. And then it goes 1s, and then the second s that's available is the 2s. And then it goes to what? The 2p. So the first P that you see is in the second energy level, or the second shell. And so if the first orbital, S, is in the first one's in the first energy level, the second orbital, P, is the one in the second energy level, the first D, which is the third orbital, would be in the third energy level. And so it's 3D. Based on that, the first F is going to be in the fourth energy level, and sure enough, if you look at the first F, it's 4F. Based on that, the first G, once it shows up on the periodic table, would have to be 5G. And so it goes just 1, 2, 3, 4, 5 like that. If we had an H out here, then the first H would be 6H, and so on and so forth. And so that's basically how you set these up and how these subshells and suborbitals work. So that's the reason why you're going to go and you go from 4s to 3d. 3d does have a little bit higher energy than 4s does. That's the reason why it fills the 4s first, because it always fills the lowest energy first. But when it jumps up to 3d, it's at a higher energy, but it's in a lower energy level. Sometimes that happens. And so that's the reason why this works. Now, we've talked about these orbitals, we've talked about the suborbitals and such like that, but really, what do they mean? I mean, we've said that S goes first, and then we go through P's, and so on and like that, but what exactly does it look like? And so let's take a look quickly at some of these electron clouds, give you an idea on what we're talking about here. This right here is a diagram of an S orbital. And s orbitals, in fact, the reason why they're called s orbitals is because when they discovered them, they were spherical, and so they called them s for spherical. And so it turned out that after they got past a few of them, they realized, well, we really don't have names for these anymore, because you'll see they get some odd shapes. So this is an s orbital. This would basically be a diagram of, say, the 90th percentile chance of finding an electron in the s orbital. And so this is basically a surface, and if I were to, say, rotate this surface, you could sort of see there's another way of drawing it out here with little dots. And so each dot, basically what happened here is the computer calculated where those electrons might show up. And so as you can see, there's a higher concentration of dots more close to the center. That's where the nucleus would be, because since the electron is negative, it's attracted to the positive protons in the nucleus. They're going to try to get as close as possible, but because of the uncertainty principle, which is this idea that you can't know exactly where the electron is at any point in time, it could be anywhere else, but it's going to be most of the time closest to the center of the atom here. But it won't quite get there, and it will be other places, other times. So this would be a diagram of what an s orbital might look like. So we've got that there. The next orbital would be the p orbital. And unlike the s, which we said only has one suborbital, so we're seeing just the one s suborbital right there, the p is going to look a little bit different. So we will go to a p orbital right here. And if you notice, it's a little bit larger. We popped out, and all of a sudden we get something that's over the size of the screen. I'm going to have to zoom out to be able to get to it. And so I'll zoom out there. The reason why is because since it's a higher energy level, that means it's farther away from the nucleus. Remember, they want to fill the ones that are closest first. So this one's farther away here. This is a particular p suborbital. Now, it looks right now just like the other one did, didn't it? Just like the s orbital. But if we rotate it, you can see it is nothing like the s orbital. It is basically two-lobed. And so let me change one quick thing here so we can see a little bit about how these guys look. Okay, there we are. And so this right here is one of the p suborbitals. And so you can see it's got sort of two lobes on it. The nucleus would be basically dead center right about in there. So you can sort of see that it's basically sort of this double lobe type thing. What will basically happen is what we're saying is the electron has sort of a 90% chance of either being in this lobe or being in this lobe. We don't know which one. It actually turns out it has a 0% chance of being on the plane that goes right dead between them, that sort of that separates these two. The electron actually jumps back and forth, or at least the probability sort of jumps back and forth in something that's called tunneling. But so this right here would be an example of one of our p suborbitals. Now we said the p orbital has 3. It has 6 electrons that it can fit total. That means 3 suborbitals. So let's see where those go for. So we've got this one right here. We're going to reset it back to the position. We're looking at sort of end on right now. As we said before, you can sort of see that there it is right there. So we're looking at end on. Let's take a look at one of the other p suborbitals. And so we'll do that. And it looks a lot the same. The only difference is the previous one we were looking at end on. This one we're looking at it from the side. It's sort of horizontal, and we've got it from the side here. Now if we look at the other p suborbital, you can see it looks the same, but it's oriented the other direction. And in fact, it actually turns out that that p suborbitals have they actually have names, and they are called px, py, and pz. The reason why is because if you think about it, each one of these lines up on the three-dimensional axis with the x-axis, the y-axis, or the z-axis. So this one right here would probably be the one that you'd want to call py, because it's going up and down along the y-axis here, versus our other guy over here, which would be this one, which would be the px, because of the fact that it goes along the x-axis. And then our third suborbital for the p would be the pz, because it sort of comes out of the board at you, out of the screen at you, and that's the third one of the p suborbitals. Now, so that's p. You got 3 of them. Now, if we go on to d suborbitals, we have a total of 5. Because of the way that works. So we're going to go on to look at the d suborbital, and looking at that, this is it right here. Once again, a little bit larger because it's farther out. We'll zoom out there. Now this one looks even sort of kookier than the last one. Almost looks like you got a donut and two little balloons coming out of it. And so that right there is the first of the first of the 5 d suborbitals. And so you can sort of see what that looks like some sort of weird donut type thing. But this basically says that in the d suborbital, the electron is going to be located in this region about 90% of the time. Once again, that the nucleus would be sort of right dead center right in there. And so the electrons never actually go to the nucleus, but they sort of fill this space, or their probability of finding them is going to be in this space. And so going back to original diagram there, let's take a look at the other 4. The other 4 are fairly similar. Here's one of them right here. You can sort of see the way those almost look like little beans located like that. And so the electron will be found 90% of the time in one of those 4 lobes. It will generally not be found in between those. It doesn't like to be in these regions in between. It'll sort of jump back and forth between them. And it can do that without actually having to go through the middle sections. That's one of those weird quantum mechanics things. So this is one of our d suborbitals. We'll now go to another one. And you can see this one right here, same type shape, just oriented differently. And so same type of thing right there. You get the idea on that one. And as well as we have another D. Same bean shape, same lobes, just oriented once again differently. And then our last one is very similar. Is that once again it's the same type of thing, same shape, just oriented a little bit differently. So those would be your D's. You could even go up higher and say, if you want to look at the F's get even weirder. So here's one of our F orbitals. So even more strange out there than the last one. And so it's got like a double donut type thing going on. So the electron would be located somewhere in here. Looking at some of our other F orbitals, F suborbitals. Here's one, more beans. So the electrons jump across through there. Same thing if we go on to our next one here. This one's a little bit different, but still you got the same ideas. The electrons are 90% of the time, if it is in this particular F suborbital, be in there. Now we could even go up to things even more complex, like say the G. Actually, let's look at our last F first before we go into G. And so here's our last one of our F's. Looks like the Walmart logo. So that's what we've got there. And looking at G, G's get even more complex, especially this first one. Oh, I can't even see that one. It's not even working out. Looks like that I've zoomed out so far. I'm not quite getting it to work on this one. But actually, let me try. There's a little trick I can do here. If I remember what it is, let's change the mass to 14 and zoom in. Will that work? Nope. I was thinking that might work here, but oh, I didn't change the number of protons. My bad. There we are. All right, so here's our first G. It's like the Michelin Man sort of going there. Got 3 donuts, and then you could sort of take a look at what happens for your other suborbitals. So we get one that looks sort of like this. We get another one that looks like so, almost like some sort of weird beach ball. Another beach ball oriented differently once again. And then sort of some looks like an orange like that. But this space just gives you an overall idea of what some of these suborbitals look like, some of the shapes that the electrons, electron clouds, tend to go into. These are all basically calculated mathematically. That's the way the computer does it here. But it says when we actually have tested this, it turns out this is really what the electrons are doing in atoms. Makes it a lot easier if we thought of them doing orbits, but they actually don't do that. They do this. So that just gives you an idea. And for more details on this, we're going to go on to our Part B on this unit, which is our Part B on this lesson, which will be on electron configuration, orbital box diagrams, and blank on the term, electron dot diagrams, sort of the actual details of how you figure them out. That's going to be this next lesson.